Welcome to Brain Vision.
In this example, we're going to be looking at energy and heat transfer. And I'm going to be looking at a runner who's jogging on a hot day. Right, so our runner has a mass M of 68 kilograms. He has a surface area, I'll say the AS, of 1.85 meters squared. His body produces energy at a rate, I'll call this EV, a rate of 1300 watts. And 80% of this energy produced is going directly into heat. Say 80% of that will be heat. This jogger has a skin surface temperature of T, I'll call that TJ, 33 degrees Celsius, and he's running outside and the temperature of the air, TA, is 40.0 degrees Celsius. So given this information, we want to calculate how much heat is produced in the runner by jogging, how much heat is transferred to him through radiation, so through the hotter air temperature. We want to find out how much he needs to sweat and have his sweat evaporate to cool himself down. Okay, so let's look at the heat produced by jogging first. We know he produces 13 watts of total energy, and we know 80% of it's going into heat. So the heat from jogging is just 1300 watts times 0.80. That equals 1040 watts. So that's the heat produced by the act of jogging itself. Okay. Next, I want to find the heat per second due to the radiation. Right, and for that, we're going to use this equation for the rate of heat flow for radiation. So H equals A epsilon sigma times the temperature of our body surface to the fourth power minus the temperature of our environment to the fourth power, right? In this equation, A is our area, surface area, E is emissivity, it's 1 for our runner. Sigma is the Stefan-Boltzmann constant, and that is given as 5.67 times 10 to the negative 8 watts over meters squared Kelvin to the fourth. Okay, and we have all these values. We have our surface area, that was our 1.85 meters squared. Emissivity is E. Sigma we just gave a value for. Temperature of the body was 33 degrees Celsius. Temperature of my environment is 40 degrees Celsius. Make sure you convert these two temperatures into Kelvin before you do this calculation. Okay, but putting in all our numbers, I get a heat absorbed by the runner from radiation equals 87.1 watts or 87.1 joules per second. Okay, next we want to determine how much excess heat this runner must get rid of per second. That's easy. That's just my heat rate from running, which we said was, all right, 1040 watts. So 1040 joules per second plus 87.1 joules per second gives me a total heat of 1127.1 joules per second. Right, so every second, to account for this excess heat, our body must find a way to lose heat, and that is by evaporation of sweat. What we want to find is how much sweat must we evaporate per minute to get rid of this excess heat. Right, and we're given the heat of vaporization for water, LV, equals 2.42 times 10 to the 6 joules per kilogram. Okay, next we're going to find the heat generated through running over 1 minute. So that's H, I'll say M equals 1,127.1 joules per second times 60 seconds per 1 minute equals 67,626 joules per minute. And that will have to equal the heat lost as liquid water turns to vapor water. Right, so that's just LV times my M, and that'll be in kilograms. So M equals 67,626. That was joules per minute. And that's the heat generated total on the runner, divided by the heat of vaporization for water. That was our 2.42 times 10 to the 6 joules per kilogram. I get the mass needed to evaporate every minute is 0.0279 kilograms, or about 28 grams, about an ounce. Okay, so just a quick example on some heat transfer and energy relationships.